not removed.
Thank you, Peter. So the holy grail of power management is setting every idle modules to sleep. It sounds very easy, but it's incredibly hard in practice, especially for mobile devices. The reason is there are so many modules on a mobile SoC. So this is the block diagram of TI-OMF4, which is introduced by Robert. It's used on Google Glass, and it's also used on Kindle Fire and Samsung Galaxy S2. So as you can see, this SoC contains a lot of modules, such as DSP and face detection unit, a lot of IOs, and each of those blue blocks represents one or multiple modules. So currently, it's their device drivers doing power management for each of them. So you can imagine it will be very hard to ensure every device drivers is doing power management correctly. And you may ask, why are those SoC modules important? The reason is they account for a large portion of the SoC. So in this photo of TI-OMF4, this red rectangle shows how small a portion the dual-core Cortex-A9 CPU occupies. So in today's talk, I will first introduce the state-of-the-art power management on SoC, and specifically I will point out what device drivers role in it. Then I will show some empirical evidence that device drivers are doing a bad job in terms of power management. And finally, I will present our solution to the problem. So let's first look at the power management support provided by the SoC. Modern SoCs are divided into resource domains, which consist of a group of modules that share the same resource, either clock or power. And each of these resource domains can be set to low power state to save energy. For example, the power domain can be completely power off or partially power off, which is termed as retention. The power domain consumes more energy in retention state compared to in off state, but it can transition back to the on state much quicker. And you may have already noticed the domains are hierarchical. Yes, the power domain encloses several clock domains, and the clock domain encloses several modules. And on some SoCs, there can be even more layers of domains. The important thing is they are also managed hierarchically. So this means the transition to low power state always starts from individual modules. So software is responsible to disable an idle module. And when all the modules in a clock domain are disabled, hardware will automatically gate the clock domain. And when all the clock domains are gated, hardware will automatically transition the power domain to a low power state, which is either retention or off. And this is pre-configured by the software. So now let's look at the software side. How does the software decide when to disable a module? So basically, software needs to take two things into consideration. The user's QoS requirements. QoS stands for quality of service, and whether the module has more pending tasks. So for the QoS part, Linux provided the PM-QoS framework. This framework will collect users' QoS requirements, such as what's the maximum tolerable wake-up latency, and it will notify the device drivers when the QoS requirements change. And upon receiving the QoS notifications, device drivers will adjust some power management parameters to fulfill the QoS requirements. For example, the device driver can choose a longer idle timeout or a shallower low power state so that the module will be more responsive. And to check whether a module has pending tasks, Linux provides a framework called runtime PM. So this framework has several APIs, such as PM runtime get and PM runtime put. These APIs will increase or decrease an internal reference counter maintained by the framework. Device drivers are responsible to call these APIs at the appropriate time so that the reference counter will remain larger than 0 when the module has more pending tasks and reaches 0 when there's no more pending tasks. Because the runtime PM framework will try to disable the module when the counter reaches 0. So in summary, software, or more specifically, device drivers, are responsible to disable an module based on users' QoS requirements and whether the module has pending tasks. And hardware will in turn transition the resource domains to low-power states when all the enclosed modules are disabled. So clearly, device drivers play a very important role in power management, but they can be buggy. And here are some problems we have found. First, we find that power management sometimes comes as an afterthought to those vendor developers. So in this timeline, there are 5 modules that had delayed power management support. And as you can see, the smallest delay is like 12. It's also 1 year. And all these modules are always kept on when the device was on, before the power management patches were released. So these power management bugs affected all the phones and the tablets that use these 2 very popular SoCs. And the second problem is, even if some drivers have power management support, the implementation can be suboptimal. So for example, for the GPIO module on OMAP 4, a proper power management will only enable the device when the CPU is accessing its registers. For example, when the CPU is setting the GPIO's direction, or when the CPU is setting the GPIO's level, or when the CPU is reading its interrupter status registers. However, we found that the actual device driver will enable the GPIO module in its probe function, which will be called during system initialization, and it never disables the module afterwards. So this means the GPIO module never sleeps during runtime. This example shows even for a module as simple as GPIO, device drivers can do the power management wrong. And making things even worse, the hierarchical resource management will magnify the power waste caused by a single device driver. So for example, the power waste caused by the GPIO module may be very small, even can be negligible. But because it keeps the entire clock domain and the power domain always on, so it may cause like 70 milliwatts waste, which is non-negligible. It is like 5% of the idle power of the phone. So we have seen device drivers can have delayed the power management support or suboptimal support, and the hierarchical resource management will magnify the power wastes. And you can find more detailed examples in my technical wiki. So what can we do? How can we avoid those bad drivers? Option 1, we can try to find better driver developers. But honestly, those developers are already expert coders and the gurus of their SoCs. I admire them myself, so you can hardly find any better men to replace them. So we offer option 2, which is automatically doing power management out of those modules device drivers. So is this possible? Let's first check what is the essential information required to do power management. First, one needs to know what's the user's QoS requirements. And second, one needs to know statistics of the module when it's in a low power state. For example, how long is the wake-up latency for a module in a particular low power state? And lastly, one needs to know whether the module has pending tasks. And we observed that the first piece of information is provided by users. So theoretically, you can make it available anywhere in the device, in the kernel. And the second piece of information is just some static information. You can obtain it from the spec sheet or do some offline measurements. only the third piece of information, it is generally regarded to be only available in device drivers. However, our key insight is even this piece of information is also available outside of device drivers. It can be obtained by monitoring the access to the module's registers, because we observe that when a module has pending tasks, CPU will frequently access its registers. So let's take the APSYS module as an example. So when the APSYS module has pending messages to transmit, the CPU will first configure the APSYS module by writing to its registers, like setting the APSYS message address or setting the message links. And after the transmission has begun, this APSYS will interrupt the CPU several times until the message is transferred. And the CPU has to, upon receiving the interrupt, the CPU has to read the interrupt status register to learn the type of the interrupt. And it also has to write back to the interrupt status register to acknowledge the interrupt. And the CPU may also have to reconfigure the APSYS module based on the type of the interrupt. So the point here is, frequent register access indicates a module has more pending tasks. So now the problem is, how can we monitor the register access? We utilize the fact that all the registers are memory mapped on ARM SoCs. So we use a monitor to periodically remove the read-write permissions of the memory region that is mapped to a module, so that next register access to the module will cause memory exception and thus be captured. So this is a very classic trick used by page swapping algorithms when they try to count the page references. So more specifically, for a module that has already been disabled, its next register access will cause a memory exception. And our monitor will notice the memory exception and then infers there's a new pending task for the module. And the module needs to be enabled. And for a module that has already been enabled, our monitor will periodically remove its read-write permissions. So if the monitor observes there's memory exception, then it knows the module is still busy and needs to be keep enabled. Otherwise, if there is no memory exception for an entire period, then the monitor knows the module has no more pending tasks. And in our current implementation, we choose the period to be 100 milliseconds, which is based on our heuristics. So based on this monitor, we build a central PM agent, which is a kernel module. So basically, the monitor will inform the controller whether the module has more pending tasks, and the controller will calls the power management callbacks registered by the device drivers to enable or disable the module accordingly. And these PM callbacks are the only modifications that's required to be done in device drivers. And it's a very simple modification. All the developers need to do is to export the PM runtime getPut functions with their own device struct as input. Also, if the device drivers are very confident that they can do power management better than our central PM agent, they can choose not to use our service by not registering the PM callbacks. And in our current design, the QoS is still left to the device drivers because we think it's a relatively easy task, and we haven't seen any significant benefit of doing it centrally. So here are 3 design principles of our central PM. First, we do not let driver developers contribute any code to our central PM agent, so we can prevent buggy device drivers damaging the power management operations. The second, we keep the driver developers' burden to the minimum. All they needed to do is register the power management callbacks in their driver pro function. then everything else is handled by our central PM. And also the device drivers can choose not to use our service. So we ran some preliminary evaluation. The platform we use is Thunderbolt, which uses TIO map 4460. The operating system is Android, the narrow Android 13.10 release. The kernel version is 3.2. So we use our central PM agent to control 4 modules. The I2C and the SDIO module, which is used to communicate with the Wi-Fi NIC on the Thunderbolt. And also the MMC module, which is used to interface with the SD card. And finally is the display controller, which is part of the display subsystem. So we run some 600 long workload on each of them, and measure for how long time they will be disabled to save energy. So here are the results. So for the I2C and MMC module, their device drivers have very good power management implementation. The red bar shows the time the module will be disabled when it's controlled by the device driver. And the blue bar shows when it's controlled by our central PM agent. As you can see, they are very close. So it means our central PM agent is equally effective as those device drivers. And for the SDIO and the DIS-PC module, their device drivers only implement some very coarse-grained power management code. So they will be always kept on during the workload. And in contrast, our modules can disable these 2 modules. Our central PM agent can disable these 2 modules for a significant portion of the time without breaking any of their functionalities. We also measure the overhead of our tool. So the major overhead will come from the memory exception. According to our measurements, the overhead, handling 1 memory exception will cost 2,500 cycles, which is 2.5 microseconds if CPU is running at 1 gigahertz. Note that this memory exception will only occur for each module for at most once every 100 milliseconds. So we think the overhead is quite low. So admittedly, this is a workshop paper, and our solution still has some limitations. So for example, the pending task inference algorithm does not work well for computation-intensive modules like DSP or GPU, because those modules can work for a long time without CPU accessing their registers. So we are currently working on providing hardware support to help the pending task inference to replace the register monitoring completely. So basically, we are adding a busy idle register to each module. This register will be set whenever the module is busy and only be reset after the CPU has read it. Then we will use the software monitor running on CPU to periodically read this busy idle register to infer whether there's pending tasks. So this approach will not only be more accurate, and it will also completely eliminates the overhead caused by memory exceptions. So we are prototyping our design on FPGA, and we wish to prove only very small hardware modification is required to add such a busy idle register. So in conclusion, our work shows that device drivers are doing a bad job in terms of power management. And because all the information required to do power management is available outside the device drivers, so we design and implement a software central PM agent to automatically power manage modules outside of the device drivers. And welcome to check my technical wiki, where you can find more examples and my experience with SoC hacking. Thank you.
So do you think different modules have different PM algorithm or the same PM algorithm? So if you move the decision into the kernel, not in the driver, so the kernel has the same PM algorithm for all the modules. Right?
Yeah, by PM algorithms, you mean I think you mean the quality of service part, right? So for example, maybe one module wants to stay awake, so it can be responsive. Is this what you mean by PM algorithm?
Something like when to turn on or turn off, or check the idle time and the busy time. So
yeah, so in our work we show that by monitoring the register access, we can differentiate whether the module is busy or idle, right? But some device driver may want to keep the module active even if it's idle, right? That's what you mean.
Yes.
So this is in the quality of service part, right? So this is quality of service, right? Because you want to make the module more responsive. So currently we still leave the quality of service to device drivers, so we don't touch that part. But we can do it. We can also move it to the central PM agent. It will not cause any problem.
Right. Fundamentally, energy management, energy is a global resource. Energy management, at least the policy should be global.
Yes.
So what you do makes a lot of sense, and I actually think your results are underestimating the benefits of this approach.
Yes,
because it should really be a centralized decision that a driver can't possibly make. You have to propagate a central policy into the driver and update it, etc. So it's much better to do it centrally.
Yes, and actually for those resource domains, because they have dependencies, so only a central PM agent will have the whole picture, right? So it's beneficial to do it in a central PM agent.
There's actually a question whether you have non-local trade-offs in these systems. I can't think offhand of one where it might be possible to spend some more power or energy in one part of the system to save it somewhere else. I'm not sure on a phone or something where that. I can't think of an example of that. But if you had these kind of trade-offs, then it's impossible to do it at the driver level. It had to be done.
Yeah, that's a good direction. Thank you.
My question is about not just the quality of service you just mentioned for the delay, right? So if you turn off that component and when you turn it on, it will cause some delays. We understand that part. But it may also cause more energy consumption because you use some minimum energy to keep it warm. Otherwise, you turn off it and turn on, and when you turn on, you have more. So that kind of thing, sometimes you have some trade-off to decide because you have to predict what would be the next task to come, how close, how far away, so that you can go to sleep. So my question is, this then is somehow related to different component driver materials, things like that. So for the idea, I like it, but how do you have that kind of knowledge for different components regarding those materials?
So a simple answer is I don't have that knowledge. Only device drivers can provide that.
Exactly. So
yes. So that part is we will call it.
How do you do that decision?
Yes, but we will call that part as a mechanism because it's just some static information, right? You just needed to know how much power will the module consume when it's powered on, right? So we think this is an easy task. So what we do here is trying to automatically infer whether a module has more pending tasks. And we think that is the tricky part of power management. Because you need to read the entire driver, then you can understand whether the module is busy at this moment or idle at this moment. Right? So we think this is the heaviest burden of device driver developers. So we are attacking this problem. And the question you are talking about, we think it should be relatively easy, and it can be done by the device driver developers.
Okay. I think you've actually been too nice to device drivers and developers. They're the crappiest code we have in our systems. The less you give them to do, the better.
Just a quick question. So in your results, you showed that you could turn off the display or the screen for like almost 50% of time, right?
Mm-hmm.
Compared to the originally that the screen is almost always on.
Yeah.
Yeah. So can you explain, how and why you can do this?
So basically, this is just the display controller, not the entire display subsystem. Right, so Robert also mentioned in his talk that the entire display subsystem has a 125 milliwatts static power. So that's for the entire display subsystem. I am only controlling the display controller, which is just a module inside the subsystem. So basically, we find out that when the screen is display a still image, when there is no animation, you can turn off this display controller. Right? You only need to keep the HDMI part on, so that the image will be captured there. So our central PM agent will automatically detect when there is no animation and turn off the display controller.
Okay. Last question? No? Okay. We're perfectly on time. Thank you.